Welcome back to ECE 501B. Homework 3, I believe, is available, and it's not due until a week from Friday. This Friday's the 19th, next Friday's the 26th, so you're sort of getting a couple of weeks to do this one. But our exam is the following Wednesday. Exam number 1 will be Wednesday, October 10th. That's, I think, when it was scheduled on the syllabus, so we'll try to, what did I say, October 1st? I saw the 10, thank you. I was going to say, what is wrong? Oh, yes, I misspoke. So it's 10/1/14, October 1st, which is Wednesday, October 1st. Thank you for waking me up. Today what I want to do is continue with Chapter 3, which is linear maps. And we barely started talking about this concept of a null space, and we want to get comfortable with that. The null space is a subspace, and it's a subspace of the domain vector space, V. We also can talk about injective maps. We'll define what that means and show how it's actually connected to the null space, and if you want to know the connection, it's because injective has an N in it and null space begins with an N. No, but that's one way to maybe keep them straight, because we will talk about surjective maps, and that deals with the range space, and that has an R in it. So if you're getting confused, injective, surjective, just go null space, range space, which is like the other, and injective is connected to null space, and we'll show, or we'll state how the connection is made and see the implications of that in a minute. We'll do the same with the range space. We'll define it. We won't show that it's a subspace. That's in the book. You can see that for yourself, but we know what has to happen property-wise for it to be a subspace, which is what? It has to have 3 properties, doesn't it? 3 properties. Good. If you're online, you can't see that I'm at fault again, but 3 properties. What's the first property? It has to be non-empty, or it has the 0 vector. It has to be closed under addition. And if you have those 2, you better be pretty easily led into the closed under scalar multiplication. Those are the 3 properties a space has to have in order for it to be a subspace. And the range space will be a subspace of the codomain, which we label as W typically. I don't know if we will get into properties of these maps and this relationship between dimensions of the different spaces, the dimensions of the null space and the dimension of the range space. Those actually sum up to equal the dimension of the domain. We'll get maybe that far, but I don't know. And then we will start talking about maybe something that you're used to thinking about when you talk about range space and null space, and that's matrices. And we've been very general or abstract with our notation and our definitions of linear maps, and we can then specialize those to form or into a matrix representation. This is what we had talked about last time, I believe, the null space. The definition is given a linear map T, and somebody has to tell you what that T is in terms of a map. T doesn't really tell you anything other than it's a linear map, and we indicate that a lot of times by saying it's an element of this script L, open parenthesis, V, comma, W, close the parenthesis. That would then tell you that T is a linear map. What it really is as a map, you may have to be told more information. But the null space of T, and I may write that many different ways. I may say the null of T or script N of T. That's now this set of vectors in the domain that map to the 0 vector in the codomain. And if it is non-trivial, meaning something more than just the 0 vector, then I've indicated that by having this bigger blue blob in our domain. But if the null space is a subspace, we know for sure that it has to have the zero vector. But it may be non-trivial. That would be sort of the trivial null space, to have the zero vector. A non-trivial means that we now have something more in the domain that is mapping to the zero vector in the codomain W. Let's look at some examples of null spaces. And these will be more abstract than maybe if you were taking a beginning linear algebra class. Let's look at the differentiation map. So that T is taking, let's say, polynomials over the field of reals into polynomials in the field over the field of reals. What is the null space of T? Well, if we simply looked at sort of the definition, we could say, well, that's these polynomials P such that TP is equal to 0. That's the definition of the null space, where P belongs to the set of polynomials. But we could actually write that maybe a little more descriptively. We could say, well, the null space of T as an operator, which is the differentiation map, on the set of polynomials that always returns 0 at the output will be what? What happens when you differentiate something, or what do you need that when it's differentiated it always maps to 0? Constants. So if we have constants, then those will form the vectors in our null space of the differentiation map. Meaning we could say, oh, this is A such that A is a real number. And in this case, we're saying that this is really just the set of constants where we're saying our polynomial P of X is simply A. And that's a null space of a linear map, where the linear map is the differentiation map. All of these polynomials, that glob that live in the null space, are all the constants, all the real numbers in that set of polynomials. What's another example? Suppose we look at dimension changing, where the map T, let's say, takes us from 3 space to 2 space. For example, let's say that we have a map on a 3 vector x, y, z, and that now takes us to 2x minus y plus 3z, comma, 7x plus 5y minus 6z. This is the definition of a linear map that changes the dimension. Excuse me. We're going from a 3 space, or a point in 3 space, to a point in 2 space by this relationship of x, y's, and z's in the different coordinates of R2. And in order to find the null space of this mapping, what points x, y, z are such that you combine them or you place those into these relationships on x, y, and z will yield zeros. That's what we mean by the null space. We want to know then what points x, y, and z that belong to R3 map into the zero vector in R2. Where R2 is our codomain. What is that meaning, or is that, what does that really imply? If you needed to find the null space, what is one way that you could approach that problem? So now you're setting those coordinates on the right-hand side, those two coordinates in R2, you're setting those both equal to 0, and hopefully they have a solution for those two sets or those two equations being equal to 0, or those two equations being true. We now need to satisfy, or we need x, y, and z to actually satisfy 2x minus y plus 3z equals 0 and 7x plus 5y minus 6z equals 0. Hopefully I wrote those down consistently. And what do you think by looking at that? Is that doable? Do we need a third equation? What did we have? We were mapping something in 3 space. We were going from R3 to R2. So we need these points in R3, and let's say the coordinates in this room. So if we walked around in this room and stood somewhere, and you looked at my head, that's some XYZ location. You want to know, is that in the null space? If we took that point, would it map to the 0 vector in R2, basically in a plane? Meaning we really just have these two coordinates to deal with. We have 2 equations, 3 unknowns. How easy will that be to have a solution? Is it possible? So now if you pick z equals 0, then what will you get? Then you get 2 equations, 2 unknowns. Why don't we just pick y equals 0? Then what do we get? Z equals 0, y equals 0, x is equal to 0. The trivial solution, right? So that would actually satisfy this, and that's something you might check just for grins, is say, is the trivial point going to be there? And it should if it's a linear map. But we want to know, is there a non-linear combination of x, y, and z that will make this true? We're now saying, or you could have written this maybe in a little bit more abstract manner. You could have said the null space of T is now equal to the set of x, y, z belonging to R3 such that 2x minus y plus 3z is equal to 0 and 7x plus 5y minus 6z is equal to 0. And I'm going to leave that to you. Is that doable? even though that's scrunched on the right. That's supposed to be equal to 0. I have an infinitely wide piece of paper. I shouldn't have problems squeezing anything in. You might. But now what I will give you is I'll give you the answer in the back of the book. How's that? It can be shown that the null space of T is equal to the span of minus 0.5294, 1.941, and 1. And that's actually an approximation. If you do the algebra, it actually is this span of minus, what is it, 9/17, and it's 33/17 and 1. Those are the points that form or you're now interested in that particular direction, that anything in that direction will actually be in the null space of that linear map. And you could do it similarly to what was suggested, except you don't want to start setting things to 0 necessarily. You could put that first equation equal to y pretty easily, substitute that y back into the second equation, and now you have one equation and two unknowns. You have a free variable. You can let one of those free variables, or you have one free variable, let's just let that free variable be z. Let's let that free variable be 1, and that's where that 1 comes from. And now you can back substitute in and find all those other values. That's how you would solve it. And you should do that just for grins tonight, to make sure that you make sure I'm doing my algebra correctly. Let's look at another null space. Suppose we have a linear map T that will map 3 space, now not dimension reducing, but dimension expanding. Let's map that into R5, where now T of x, y, z, and you'll notice that sometimes I write it as a row vector, sometimes I write it as a column vector, but hopefully it's okay however I write it. This now is going to map into a 5 vector via minus x plus y minus 3z minus x plus 2y minus 4z, x plus y plus z, 2x plus 3y plus z, and finally x plus 2z. And we want to know, is it possible to find some value or values of x, y, and z that actually force all 5 of those rows to vanish or to become equal to 0. For the null space to be non-trivial, we need the right-hand side to be the 0 vector for some v in R3, where v is x, y, z. And if you actually look at that, you can show that the null space of T is actually going to be spanned by this combination of x, y, and z, minus 2, 1, 1. That will simultaneously satisfy all of those And any linear combination of -2, 1, and 1, and we now know what a linear combination of that is, or a scaled version of that is. We scale that by some real number, and that's going to be in the null space of that linear map T. Those points x, y, z. Now this one's a little non-traditional, meaning we typically don't go from a small dimensional domain to a higher dimensional codomain and expect to necessarily find a non-trivial null space. That's not that easy to do or not that common. So when I say note, this is sort of saying this may not be that common. The dimension of R3, which is actually our domain, how big is R3? Dimensionally, that's 3. And that's actually less than the dimension of R5, which is 5. And it's not typical that you have a non-trivial null space under those conditions, where you have more equations than you have unknowns. Let's now look at this concept, which we haven't yet shown, but we talked about it earlier for the range space. Proposition, wow, it's just the first proposition in chapter 1. We've just now gotten to the first proposition. We'll have to hurry up, maybe. Proposition 3.1, the null space of a linear map T such that V is taken into W is a subspace of what? What are my options? When we talk of a subspace, we're now saying what vectors in the domain map to the 0 vector in the codomain. So this has to be a subspace in the domain, which is V. This is now the null space of a linear map T from V to W is a subspace of V. And we can show this. Like I said before, we may not show this for the range space, but let's go ahead and show it for one of those. And you told me earlier that the subspace, or to be a subspace, it has to satisfy those 3 properties. A subspace must satisfy three properties. One is that it's non-empty, or it contains the additive identity. So we have T of 0, but we know that we could add 0 to 0 and get 0 back. So let's do that. We now have T of 0 plus 0. This is now the additive identity in V. But by the additivity property of our linear map T, that says that we have T of 0 plus T of 0. And that says then that we have 2 times T of 0. But if something is equal to twice something, what's that something? 0. So now we know then that t of 0 must be 0, which is the 0 vector in our codomain W, which says then 0 is an element of the null space of T, where this 0, have a lot of zeros floating around, where does it live? In V, as we said before. All right, we have the additive identity for, or it's in the null space. The second one is we need this property to be true, and that is to be closed under addition. Here, let's say we're given U and V, both belonging to V. Whoops. No, let me say that they are now both in the null space of T. So we're given two vectors in the null space of T. We now say, well, what happens to the sum of U plus V when we operate on it with T? And by the additivity of the linear operator, we know that's equal to T of U plus T of V. But we were given that U and V both were in the null space of T, so this is 0 plus 0. And 0 plus 0 is just 0, which is in W, which says then that if we look at the far left-hand side, U plus V must be in the null space of T. And so it's closed under addition. Finally, the property of closed under scalar multiplication can be verified. Here we say, well, let's suppose that we're given some vector U that's in the null space of T, and we are given some scalar in our field of numbers, F, which could be R or C, real or complex. Suppose we now look at T of AU. Well, we know by homogeneity that that must be A times T of U, since T was assumed to be a linear operator, so it has to satisfy this property. But we knew that U was in the null space of T, and a scalar, any scalar times the 0 vector gives us back the 0 vector. We're back then in or at the 0 vector in W, which says, if we look at the far left-hand side in this equation, that when we started with U in the null space, any A times U is also in the null space. We now have all three properties, and so the null space of T is in fact a subspace of V. Now let's introduce a new term, injective, where we'll focus on that in injective. That's why it's underlined. Definition. Given a linear map T, that's the way we've defined a linear map, if whenever U and V are both in V and the linear map applied to U is equal to the linear map applied to V, if those two results imply that u is equal to v, then the map is said to be injective. Or one-to-one. So now, whenever we have the result of our linear map from two different vectors, let's say u and v, those results are equal. If the map is injective, that means that the two vectors that you started with had to be the same. So that you get the same result for any one point that you start with, or any vector that you begin with. It's one-to-one. You give me a vector in v, that will only map to one point or one vector in w. Now, we already, by definition of this linear map, had said that t of u for any u gave us a unique vector. So t of u already selected a unique element in w. Now, in an injective map, only a single element of v maps to that unique element in w. Meaning you can't be in this domain at two different points, go through this linear map and end up at the same location or vector in your codomain. That's what this is meaning. You start at one place, you go somewhere. You start at a different place, you go somewhere else. It's one-to-one. And I like to draw a picture. There is a one-to-one relationship between the elements of v and w. Meaning if we had v over here and w over here, then if we map with t, if we start there, we're going to end there. If we start here, we're going to end there. We start there, we're going to end there. We're not going to the same point from two different locations in our domain. Another way of thinking of this in a very two-dimensional framework would be to say, oh, if this is now x belonging to v, then to be one-to-one or injective, we really need the mapping to be such that if we drew a horizontal line, it would only intersect that mapping in one point. Here is then our f of x in the codomain And the red line then says that each horizontal line only passes through one point on f of x. If that was not the case, if our function sort of had some bends in it to allow our horizontal line to go through 2 points, then we could find 2 intersecting points that have the same value in our codomain that have different values in our domain. And that's not what we mean by one-to-one. Meaning we could get to the same point starting at 2 different locations. That's what this picture is supposed to provide you with in terms of the insight. Now, we can actually connect these 2 concepts of injective map and null space. There's a strong relationship between the null space of a map and whether the map is injective. And if we have a strong relationship, that means we must have a proposition. So here's proposition 3.2. And it says, given a linear map mapping between V and W, that linear map is injective IFF. That's not BFF, it's IFF. If we're texting, don't get a T or a B in there, it's an I. I don't even know what I'm talking about. But this means IFF I do know. That's if and only if. T is injective if and only if the null space of T is the 0 vector. Not the empty set, but the 0 vector. So we have to have a trivial null space, or we have a trivial null space if and only if the linear map is injective. That's the strong connection between these 2 concepts of an injective map and a null space. Since it's a proposition, we better prove it. Let's see if we can. And one way to prove if and only ifs are to start with one statement, show the end statement, and then just the opposite. Start with the other statement and show that it implies the beginning statement. To prove an IFF, and I think IFF was around before BFFs were, just if you were curious, wanting to know the timeline. To prove an IFF, we're not proving a BFF. If we're proving an IFF, have to show, well, I guess a BFF is sort of the same way, right? One implies the other, and the other implies. All right. So we have to show implication in both directions. First, so we're going to have 2 parts to this proof. The A part is, let's assume the linear map T is injective. What does that mean? That means if T of U is equal to T of V, then U equals V. That's what an injective map means. So if T of U is equal to T of V, that means U is equal to V. And we're assuming that now. Now let's just go ahead and pick a vector V in the null space of T. If that's the case, then what's T of V? 0. We were just given that. We're letting that be true. That says that V is in the null space of T. But what else do we know? Remember from the previous proof, the null space is a subspace. That means that 0, the 0 vector, must be in the null space of T. So from the previous proof, we know 0 is an element of the null space. And 0 is in V. It's in the domain. So now we know that T of 0 is equal to 0. That's the 0 vector in V, and this is the 0 vector in W. Well, now we have T of V equaling 0, but 0 is also equal to T of 0. So now we have T of V is equal to 0. We let V be in the null space, but now we've shown that T of 0 is also equal to 0. But what do we know about an injective map? If we have an injective map, or if a map is injective, we know if their result, T of V is equal to T of 0, that implies that the element in their domains have to equal, which means that V is equal to 0. What have we just shown? We've just shown that if we assume an injective map, that implies that the null space of T is only 0. Because we didn't specify what particular value we had for V. We just said, let's pick any vector V in the null space. And now we've shown that whatever that was, it has to be the 0 vector by the map being injected. So we've gone one direction. Now let's go in the other direction, which is B. Let's now assume that the null space of T is trivial or has this property that it only contains the 0 vector. Now let's go ahead and let U and V both be in our domain, and suppose that T of U is equal to T of V. So now we're letting UV be in V and TU equal TV. That's what we're basically given. Well, now we can use that fact that T of U is equal to T of V and say, well, that's just, if we work with it properly or subtract TV from both sides, we get 0. So we now have 0, which we can say is TU minus TV. But that's now T of U minus V by what property? Additivity of our linear map. Since we're assuming that T is a linear operator. Well, now we know that T of some element gives us 0. That means this element in the domain must be in the null space of T. Meaning now, or let me, so U minus V is in the null space of T. But we said, or we assumed to begin with, that the null space of T was the 0 vector. So now we're saying, or that implies that U minus V must be equal to the 0 vector, since it's in the null space of T. And if that's the case, then U is equal to V. And that now is what we needed for a map to be injective. We started with 2TU equal to TV, and we've shown that that implies U is equal to V. Well, that's the definition of an injective map. And we were able to prove or show that implication by assuming that the null space was the 0 vector. Therefore, T of U equal to TV implied U is equal to V. That's the definition of an injective map, which now allows us to say that the null space of T, being assumed to be the 0 vector, implies that the map must be injective. And now, because both A and B have been shown that one implied the end and the end implied the beginning, we now can say that T is injective if and only if the null space of T is equal to the 0 vector. Which allows us then to talk a little bit about what does it mean to have a non-injective map. If an injective map means that your null space is the 0 vector, then a non-injective map must mean that you have a non-trivial null space. Pictorially, this now is saying something like the following. You might start here, here, and here, and those might all end up at the 0 vector. Meaning now you might go there, there, and there for a non-injective map. Or actually you could go from many different points to something that's not even the 0 vector for a non-injective map. But now you can have multiple points going to the same location. V mapping to T in a non-injective map means that you can have many different starting vectors in the domain pointing to or producing the same location in the codomain. the null space of T is non-trivial for a non-injective map. What you may want to do is find a more explicit example, but let me just talk in general terms. Suppose we let W1 be the output of a linear map T operating on V, where V is in the domain. And suppose we have another vector U that's in the null space. And let's assume that that vector U is non-zero. Then we could actually create a new vector, Z, which is W1, what? Wake me up. I want V plus U. Now what's T of Z? T of Z is now T of V plus U. And that's now T of V plus T of U for a linear operator. And T of V, we said, was W1, and T of U was 0. So that now T of Z also produces W1. What that says then is that T of Z is W1, which is also T of V, but since U was non-zero, that did not imply that Z is equal to V. And so that particular linear map is not one-to-one. And what we've said is we started with a non-trivial null space. We said we're assuming a vector U that's not equal to 0 belongs to our null space. By making that assumption, we can show that in fact that map is non-injective. And we've said this before, but let me just repeat it. If you have a non-trivial null space, a null space that includes more than just the 0 vector, if you have a non-trivial null space, then the map is injective or not injective. For a non-trivial null space, now we can take things in that non-trivial null space, add those to arbitrary vectors, and get to the same point as if we started at that non-trivial vector to begin with. Then the map is not one-to-one or not injective. That's working on the null space. Let's now talk about the other space that we can discuss, and that's where we can get to by operating with this linear map, and that's the range. The range of a linear map L of V comma W is the set of vectors in W which are of the form W is equal to TV for any vector V in capital V. That's the range of a linear map. In a diagram, now what we're saying is if we map from if we map from V through the linear map T, then where we arrive in our codomain, or where we can get to in our codomain, we will refer to as the range of T. Meaning the range of T, which I might write many different ways, probably script R of T, are the set of W equal to TV such that V begins in our domain. So we take all the possible elements in our domain, we map those through T, and where that puts us in capital W is the range of that linear operator. And that range may be extensive, it may be very minimal, and we have to figure that out. In other words, the range of T is all the possible outputs that we can get to in W. Now, let's just recall that the null space of T was a subspace, and it was a subspace of what? V. That was the domain subspace, or a subspace in the domain. Proposition 3.3 now tells us that the range of T is a subspace, but now it's going to be a subspace in W. So now the range of T is a subspace of W. Again, you would need to show that it satisfies those three properties. It contains the additive identity, it's closed under addition, and it's closed under scalar multiplication. Then the range space is a subspace. Let's now that we have this range space concept, let's introduce another term, which is closely connected to the range space because it has an R in it, surjective for range. A map T, and here we're assuming that T is a linear map from V to W, is surjective if the range of that linear map, range of T, actually is the entire codomain, W. Then it's surjective. Or you might hear people call that surjective onto. It covers the entire codomain. Every vector in W is a possible output of the linear map T. Again, generalizing a two-dimensional picture to multi-dimensions, this could be a surjective map, where this vertical axis is W, and this map in blue says that I can get to any point on, let's say, that vertical axis. So every point from that function f goes to a point in the codomain. This range space, or what you're actually able to map to, is crucially dependent on how your linear map T is defined. Here's a good example from the book. Suppose that we have the differentiation map. Suppose that now we have T is an element of L of mth order polynomials is the domain, and suppose that the range, or the codomain, the domain is the set of all mth order polynomials. The codomain is the set of all mth order polynomials. And this is the differentiation map, meaning now Tp is P prime. Is that linear map T surjective? Why not? So the answer was no, if you couldn't pick that up on the microphone, or that was the answer from a couple of voices. I didn't hear any objection, or did I? Is it no? Or is this map surjective? So now it's going to depend critically, the comment was it depends critically on the order of the polynomial, of the domain and the codomain, as to whether or not this map is or is not surjective. The way I've written it here, it's not surjective, is it? Because I could give you, if little m was third order, I'm never going to get to a third order polynomial when I differentiate a third order. It's always going to be a second order or less. So this map is not going to cover all of the third order polynomials. It's not surjective the way that it is written. Where here I'm saying that P sub m is defined as the mth order polynomials. But the linear map T, from the domain, let's say, of mth order polynomials over the reals, to the m-1 polynomials over the reals, where TP is still the differentiation map. Do you like that one better in terms of being surjective or not? This one is surjective, isn't it? Meaning this idea of a surjective map is heavily dependent on the range and the codomain, the domain and the codomain, the choice of those. Let's draw some pictures. What does a surjective map look like? Now we have these two blobs, and this is a vector space V and a vector space W, and they are related or connected by this linear map T. For a surjective map, that means that we may not have to take all of V, but we definitely want to be able to cover all of W. So let's say that this is now the range of T, which is equal to W. That's all of W. That's the picture we have for a surjective map. We can cover everything by this linear map T from V to W. Whatever we take in V, it's going to cover. If we take enough points, it will cover W. Let me sketch a relationship, and you tell me what properties it may or may not have. Suppose this is X, and this represents f of X. Whoops. Well, hopefully you kind of get the idea. This is now the axis for f of X. Suppose this is now the relationship. So that now the range, or this map, is such that x squared, x is an element of R. Irrespective of whether this is linear or not, is it injective? Is this map injective? Why not? So now it doesn't pass the horizontal test, does it? So this is a map that's not injective. Is it surjective? Why is it not surjective? You can't go negative, can you? And we wanted our vertical direction to be the real line. So it's not surjective because the output does not produce negative numbers. Let's look at an example of a non-question. So the blue circle, so the question is beginning, and it's, no, is that what you're saying?
Yeah.
You're just trying to clarify this diagram?
Yeah, at some point in the domain that you don't fit forever.
You, how do I want to say this? You may not, they may be, I can't say, they may be extra. You may not need them. Yes. So then it's meaning that it's not injective. You might be able to take a point here and go to that same location. So this is sort of the contrast of surjective versus injective. So you could use all of these points in blue to fill all of W, but you don't need all of the V to fill W. But you can use more points in V. Those are sort of extras, and they will also map into W. Let's look at a non-surjective map that, let's say, is a linear map now. T is going from R3 to R5. And we've already seen this one before. This is taking a point in 3 space, x, y, z, and it's mapping that into 5 different coordinates. Minus x plus y minus 3z, minus x plus 2y minus 4z, x plus y plus z, 2x plus 3y plus z, and x plus 2z. Now before we were interested in what points x, y, z map to the 0 vector. That was concerning the null space. Now we're concerning the range space. We want to know where can x, y, z take us in this 5-dimensional space. Where can we get to? And it should be obvious. It's just a 5-dimensional vector. That W equal to TV actually gives you a span of the following list of spanning vectors. -1, -1, 1, 2, 1. That's just x, isn't it? And setting y and z to 0. We could set x and z to 0 and get 1, 2, 1, 3, 0. And then we could set x and y to 0 and just let z be 1, and we have -3, -4, 1, 1, 2. And now any linear combination of those will span W. Yes? So now is this going to be a basis for the subspace? We're not going to have time to show this, but this is now a spanning list, isn't it? This is now a spanning list. But is it minimal? This now is, this span is the range of T. That's where we can get to by any linear or any choice of x, y, and z. But in fact, this range of T has a smaller dimension than those 3 vectors would maybe lead you to believe. The span, or the range of R, you can actually show that those 3 are not linearly independent. They depend on one another, and you can then show that the span of 1, 0, -3, -7, -2, and 0, 1 2, 5, 1 actually produce the range space also. And this is of a minimal dimension, meaning the dimension of the range of T is equal to 2, which is less than, quite obviously, the dimension of W, which was the dimension of R5, which was 5. Meaning R of T does not span all of R5. And what does that allow us to conclude about T and it being surjective or not? It definitely is not surjective. Maybe I should say a surjective map. And what we will look at, remember that's the same set of 5 combinations for coordinates that we looked at the null space. We found the null space to be one-dimensional. We found the range space to be two-dimensional. We'll pick up at that point by seeing if that makes any connection with what's the dimension of our domain for that map. 3. 1 plus 2 equals 3. We'll see if we can make that connection next time.